Good morning, everyone. Welcome to the final day of Explore. Thanks for joining our session. We're going to talk about right-sizing VCF for private AI and models and AI workloads. So my name is Johan from Amersfoort. I'm a chief evangelist at ITQ, and I lead our AI initiatives.
Hi, my name is Denneman. I'm the Distinguished Engineer for Private AI Foundation and Private AI Services.
Is the audio okay? Can you hear us?
Yeah.
Okay, cool. Right. So we have a disclaimer. Simply states that you shouldn't be buying something because we say so. What we are going to do today is we're going to share a real-life story in a real-life scenario of something that went sort of wrong, where we tried to size something and we worked alongside a third party. And the customer eventually was not happy with the result, so we had to figure out something else. And I'm kind of gonna guide you through the story and how we eventually solved it. We're gonna talk about RAG augmented generation. Who is not aware of what that is? One hand.
Who actually implemented a RAG environment? A few already.
Oh, nice.
Awesome.
Okay, cool. So, RAG applications, oh, no?
Yeah, use this.
Oh, there, yeah. RAG applications are currently the most common deployed applications, AI applications out there. It's insane if you see what the increase of AI apps is that currently is being deployed on-prem and even in the cloud. So we've been working with several several AI-focused projects for the last 7 to 8 years. And at first that was just traditional machine learning, fraud detection, object recognition in video streams. But now, since the whole kind of AI bubble bursted and exploded basically, this is basically what we see on a day-to-day basis. So on a very high level, what RAG does is 3 major things. So we combine a large language model with a specific database. We add data to that database, and we can do that asynchronously and automatically. And we have an architecture which supports multiple models for specific tasks and basically provide that as a service. So Frank, could you kind of guide us through the architecture and the components involved?
Thanks, Johan. So when we talk about RAG, it's all about adding your own knowledge to a large language model. So you can use a large language model to use your natural language to engage with your private data. However, you need to actually get your private data in that vector database to actually expose it to the users using a large language model. So to get the data in, we are using an ingestion pipeline. So what you see at the top, you see data sources. When you're using private AI services, those data sources can be SharePoint, Confluence, Google Drive, and an S3 API-compatible data store. Now, you consume these data sources, you're going to ingest that data there, you're going to crawl, you're going to fetch, and then we need to index that data. So we need to figure out what's there, what's new, what's the metadata like. We use a data framework for that. Typically, or the most common data framework used today is Llama Index. It's an open source data framework. When we grab that data, we need to be able to understand the data from a context perspective. So not necessarily we're only going to capture the words. We need to understand the meaning of the words. So think about when I say apple, do I mean the technology company, or do I think and talk about the fruit? So in the context of a sentence, we will get the actual meaning of the word. We do that with an embedding model. We create a vector embedding, and if you look at a vector embedding, it's just basically pi on steroids. So we use a mathematical equation to figure out the meaning of the word, and in order to actually search for the right words, that's what's called similarity search. If I ask you a question, what's in the database that looks the same or that potentially has the answer in it. Now, when we do that, we use that embedding model and we push the data into the vector database. What I did here is I also showed what type of compute power you need. So for the data framework, you need to have a container with CPU. For the embedding model, you need to have a container with GPU, but in most cases, you can actually also use a CPU. And then for the vector database, just a database, so typically you will have CPUs. There are some vector databases that are accelerated by GPUs, but that's something that we do not use today. Does this make sense? Now, for the people who are concerned about storage, we do random reads in the data store, and we basically push all the data as a sequential write to the vector database. This is important to know because when you do retrieval, basically ask large language model a question and we'll try to figure out whether that vector database has that knowledge. We basically do a random read on the database itself. So you don't want to combine those processes. So typically what we advise is do the indexing off hours. So it's for your organization the time that you don't have the most users active in the system. When we look at retrieval, you have your user. We basically ask the question to our GenAI app. That question is also being embedded in order to basically figure out in the vector database what type of data do I have that matches that question. We will grab that data. In some cases, we will send it to a re-ranker model. Why? Because typically you don't get one answer, you get many answers. So I can send all those answers to the large language model and basically say, hey, I've got this question and now I've got 10 answers. Can you generate me an answer? That's not optimal. What we can do is use a model that says, this is the question, these are the potential 10 answers, which one fits best? And that's the one that we're going to send to the large language model. That re-ranker model is really small. You can use it with a CPU or with a tiny GPU, so a fractional GPU. That's on our roadmap in private AI services. Large language model is typically a container with multiple GPUs. This is the retrieval process. Does this make sense to everybody? Okay.
Yeah, what's really cool is that, who saw the general session, the keynote? Good. 2 years ago, we deployed this from scratch. Built VMs, installed Ubuntu in it, attached a GPU, built some microservices, some containers. We ran basically everything, but you had to manually build it. What's really cool about this, and you can see it at the booth, there's a private AI services showcase where you basically can see this as one of the new services of the private AI services frameworks, which is just part of VCF. So it's not a dedicated application that you need to land, you need to build. It's part of VCF, so that's really, really cool. Now let's dive into the customer story and talk a little bit about the impact of AI decisions that have been made on an earlier phase. So we know for a fact that a lot of AI deployments, AI projects start with an experiment. So we just played around and did exactly that, like build an experiment.
Nice.
Okay, who has actually run it in production already?
One hand.
Okay, one hand, okay.
Nice.
So, and if you did that experiment, did you swipe a credit card or did you actually kind of deploy it on-prem? Who did deploy it on-prem? Who swiped a credit card? Really big credit card, yeah. Now, if you look at the context of the customer and kind of the idea behind the project is that we needed to deploy some form of AI, and private AI in this case, to protect IP and ensure data gravity. Because the customer is a global industrial manufacturing customer. They answer, and this is basically their business model, they answer multiple RFPs per day. It could be 10, 15, maybe 20, because they do something really, really unique. They're really good at it, and the way they work is that other companies send out those RFPs and they answer it. 9 out of 10 times they win it, but there's a lot of work involved. So they have millions, literally millions of already answered RFPs and documents that they needed to kind of go through, look at similarities, copy data from one, paste it in another. So there's a large team involved that has to do that on a day-to-day basis. So you can imagine what AI could do there. So they have a unique process that's protected through patents, but they are impacted by company espionage on a very regular basis. So the factory is highly secured, but still, like, drones fly by on a monthly basis, and it's just challenging. So the proposed solution is considered to be, well, it states business critical, but honestly, I think it's mission critical for them to deploy it in the right way. And private AI is the answer, but how? Now, we started to work with them as a kind of a cloud company, right? So we are a multi-cloud company. We build clouds for customers that they can land basically any type of application on. We're not commonly known as an AI company. So what's logical if you are a company, you have your business processes, you have your challenges, you want to solve that, you Google for an AI development company, right? So an AI company. So they work with an AI consultancy firm, and as those companies build applications, AI applications, the easiest way for them to build that is to swipe a credit card, get a public API, and make sure that the company credit card of the customer is used. So they don't care about cost. Cost is involved for the customer. So every token that's being generated is billed to the customer as well, not to the development company. So it's the fastest way to go to a POC and to share and show what the value is with great results. And they had no focus, like literally no focus about private AI. So result, POC succeeded, but yet now what? I mean, we still had a challenge. So I'm quite opinionated on some things, and this is one. I strongly believe that developers, AI-focused developers that leave university today are not used on like waiting. So they have no idea what the impact is on local infrastructure. If they want to build an application today and test it today, they want it now. I mean, like looking at the audience, the average person here in the audience knows what it is to, a couple of years ago, to rent a video at a video store. And
are you calling them old?
No, you're calling them old. No, but the current generation is not used to waiting. If they need a service, they want it now. They want to now consume it now, integrate it in their application, and get the most out of it. So let me kind of, and this is one of the challenges that the customer face. There's a big gap between developers and IT. And we already knew about the gap many years ago because this is not new, but it does have a different impact when talking about AI. Because there's a gap in expectations. And talking about the developers nowadays, they're educated to consume services and functions directly. They don't want to know what a VM is or have hardly any idea what a Kubernetes is. They just consume services and functions. Resources are unlimited because the only limit they have is the limit of a credit card, right? So I don't care if I need 1 GPU or 28, just give them, I need them, I build my application, we'll run them. And this is really important when talking about developer experience. Developer experience is one of the themes this week, especially looking at the Tanzu portfolio. The whole idea behind Tanzu is to create a perfect developer experience with ideally, if you commit a change, a build time that's under 10 minutes. That's native in cloud, but that's not native in IT infrastructure. They love a limitless credit card. And the IT admin at the other end, you know, we think cloud being private cloud, right? That's why we're here. I mean, this is the private cloud event. And we know that other people from the business, those developers, people requesting resources, think of this being a bottomless pit, which it's not. And build time, yeah, like we want to support that 10-minute build time, but then we need platforms like Tanzu to do so. And looking at the resources that we could offer to them, they're CapEx heavy. They could be OpEx, a little bit more OpEx heavy, but you know, we don't have that bottomless pit. We don't have a gazillion GPUs. So we need to kind of work with that. Now, when we want to bridge that gap, I think it's really important to have those early conversations with the people building those applications that need to run our infrastructure. We need to understand the choice for certain models. I mean, why do they pick a certain model? Why is that? And I'll explain a little bit more about that in a bit. We need to focus on developer experience, because if we don't offer that 10-minute build time, they'll still swipe a credit card somewhere else and build it cloud native. And this is really cool, and part of what we can do today is related to FinOps. So if we build a virtual machine or an application on a platform, we want to make sure that they know what the cost of such an application is. I mean, it's fairly simple to request 8 GPUs if you have them, but they have no idea what the cost is for the entire infrastructure. And this is totally part of one of the themes this week, which is the cloud operating model. Now, meanwhile, at the customer, the AI dev responsible for the application decided to use Llama 4 Maverick. Does anyone here have an idea what Llama 4 Maverick is, how big it is? Couple of hands, okay. So, Frank, would you enlighten us?
Yes. So one of the key things that people try to understand when they start out with deploying an AI infrastructure is sizing. Like, what do I need to buy in order to support my use cases? In the case of that developer, they want to use Llama Maverick, which is one of the most largest models you can download. Now, when we say large, we need to understand what that means. What does large mean when it comes to infrastructure sizing? And the way you can calculate it, but it's a very complex calculation. So when we look at a model, we need to ingest the files and we need to store it in memory, because that's the fastest way to process any question. There are two parts of memory consumption of a model. There is the dynamic part and there's the static part. Static means I'm going to download the model, upload it into GPU memory, and even if I don't use it, it will always be there, regardless of any use possible. Every model is expressed in the parameter count. So we say 70 billion or 8 billion, or in the case of Maverick, 405 billion. Now, what does that mean? A parameter is pretty much stored in a precision type. That's a long range of numbers. The most dominant one is FP16. And every parameter is stored in FP16. That means we are consuming 2 bytes per parameter. So it's really easy to understand that if I load a 70 billion model, I am going to use at least 140 gigs just to load a model. Not using it, just to load it. It's constant. But now when I actually ask a question, it's the complexity of that question that will actually generate the dynamic use. How long, or basically how many words do I use? How many input do I provide? So think about that RAG use case, what I told you about, that I'm getting 10 answers. If I basically use all those 10 answers from my vector database, that's the dynamic part, right? And then based on the way the model is created, its architecture, it's going to use a lot of cache. So, like I said, 70 billion times FP16 is 140 gig. But now, how much data am I pushing through a model, right? We have what's called a maximum context length. Pretty much that's the attention a particular model can give to you in one go. How many words can it use and process at the same time? I'm using a 30K context length in this example. That's a large amount of words. I'm using the same precision, and I'm not going to go over every single detail, but then the architecture of the model matters. So in a worst case scenario, if somebody is really lengthy in asking a question, and they use 32 tokens, that question will consume 860 gigs next to the static part. So the maximum context length is typically something that a data scientist starts to experiment with. In the amount of words, can I still use my model? If I just limit it to 10 words, you're not going to get any decent answer, right? But that's where you basically start to think about. This, on the right side, that's something that we don't expect you to understand. This is just me trying to be a level 300 deep dive, right? So this is something that we need to be able to express in a way that you can consume it. Now, let's use that example.
I got a question. But like, who visited our session last year when we talked about a rack deployment and right? So last year we showed two different models running next to each other with the same application. One with a small model, one with a relatively big model. And the application that we built was called Project Yoda. So we basically asked a RAG application a question, and we expected the answer being translated into Yodish. Now, the bigger model had a perfect understanding of what Yodish was. So from a developer's perspective, it's fairly easy. I ask a question, I tweak the model in such a way that every answer it gets back is in Yodish. But the impact is that I need a bigger GPU because the model is bigger. Whereas what we showed was a smaller model that had no idea of what Yodish was, but a basic understanding of English. We rerouted the answer to an API, a Yoda API, and let it translate that. Result is that the smaller model would fit on a smaller GPU logically, so a lower investment. And what we showed, and this is kind of the impact of what the customer had to do, or the developer had to do, is they needed to solve stuff in code and in APIs instead of just relying on a massive model that has all of the information they might need in the future, but have no idea if they would ever need it.
Yeah. So we now know like what's the static memory consumption, what's probably the dynamic memory consumption. But if you then go to the Dell website or HP website or NVIDIA website, you see these GPUs. And so the first thing that you're going to look at is the memory. Now, if they say, hey, I want to run 405 billion parameters, obviously one L40S doesn't really cut it. So you need to start to think about, okay, what type of models am I going to use? How lengthy will my queries be? And then you're going to start to think about, okay, what type of GPU is interesting? Now, the further you go down the bottom, the more expensive it gets, right? So that's also a big problem. Cool thing is, what we announced this week during the keynote is that we support for the first time an RTX device for VDI and for ML, and that device has 96 gigs. Way cheaper than a full data center GPU. So that's a good way to start to understand your use cases, and then maybe you can extend your data center to the more data center-like environments. Now, if you see all of these numbers, you know that most models that are used today don't fit on a single GPU. So you need to have the ability to have multiple GPUs in your server and possibly connect them together. So if they want to communicate with each other, or if you're going to shard the model across different GPUs, they can interact with each other with the lowest latency and the highest amount of bandwidth. There are two different types of interconnects from an NVIDIA perspective. There's the NVLink and there's the NVSwitch. I'll talk about that later. On the node side, you can see basically where they're used for. Now, I talked about a standard model, but in today's world, we're looking at mixture of expert models. Show of hands, heard about it? A few? Cool. So a mixture of experts is just a classroom full of dedicated experts, small models that really know what they're talking about. So what you do is, and the one that Johan was talking about has 128 experts, but you need to load them in order to be able to engage with them. You cannot wait and basically say, oh, I've got this question for this expert, let's get him into the room. The person or the expert needs to be there in order to respond really quickly. So from a static perspective, it's a really large model. But from a dynamic perspective, you typically use two experts. You use a domain expert, and you use a general model that can basically convert into natural language, that understands how to express itself. And that means that the number of dynamic use is not as large as loading the entire model. Again, really advanced. Typical, that's the stuff that you don't need to really understand to begin with an infrastructure. But the cool thing is, they also have a 1 million token context window. Like if you have like these insane use cases, you can end up with a 2.1 terabyte consumption of dynamic memory. That means, or I'm actually stealing your slide.
What does that mean, Frank?
So if you want to do that for one query, you need to have 3 Dell boxes with each 8 GPUs, each a B200, and each system draws 8 kilowatts. Now, maybe you've got the budget, but do you have the data center that supports that amount of system draw, of energy draw per rack, right?
So if you now know that the subscription that the customer pays for the AI application is roughly $3,000 or 3,000 euros a month, I have the idea, like what would such an infrastructure cost? 8K, 7K, 6K? That's not really in line of what the application would have cost. So we need to solve that, right? Yeah, so which model did we end up deploying? A much smaller model, simply because the application was altered. More intelligence has been put into the application. And the result is that we could just use a far smaller model that could fit on a single node with 1 or 2 GPUs, which makes the investment from a customer perspective far more realistic and in line of what they would pay for the application itself. So the total cost of ownership is much more interesting, but we had to have those good conversations with the AI developer upfront to make that work. Yeah, let's talk about multi-GPU configs.
Let's speed it a little bit up, otherwise we can show the demo. So if you look at Dell again, or HP, or whatever your favorite vendor, you're going to see multi-GPU servers. But depending on the interconnect, they can have this type of architecture. So you might have a system with a couple of L40Ss that will give you the amount of memory, but they're not interconnected with each other. So you will have a PCIe response. Sometimes that's good enough, but sometimes you are a little bit more advanced, so you need to have something with an NVLink. Typically, that's a physical connection, a plastic connector that you actually have to put into the PCIe devices. So you have some that only can do between 2 cards, or the modern ones that can actually have 4 cards. And then you go into the realm of using SXM GPUs. You don't have a PCIe device anymore, but it's integrated in the motherboard. That's an interesting thing, because typically when you talk about SXM GPUs, you automatically think everything is integrated in the motherboard. Yet, true, but some of them still use an NVLink, which is just a peer-to-peer connection. But with NVSwitch, you will have a full mesh where you can start to think about, hey, I want to really assign a particular configuration to a particular virtual machine environment. At the end of the spectrum, that's the most costly one that you can get. So the cool thing is, if you load a vGPU driver in the kernel, you need to have an NVIDIA AI enterprise license for that. We can understand the topology of your server. So we know exactly which GPUs you have in your cluster and which ones are configured. On top of that, that doesn't mean that if you have like an 8-way system, you need to assign 8 GPUs to a particular virtual machine. We can isolate a particular configuration to a particular virtual machine without impacting the other ones. We created device groups for that. So I hope you can see it a little bit, but in the middle you can see a very cryptic description saying, I got a group of 2 NVIDIA's H100s with 80 gigs of memory, or 4 or 8. And you can basically say, I want that, and then we will figure it out for you. So we will find out the host, we will find out the configuration inside the host that is as optimally as possible. So you don't have to think around like figuring out which GPUs are connected to which GPUs. Now, if we dive in a little bit more deeper, it sounds really great, but if you do this on a repetitive basis, you can end up with fragmentation. Because not every workload is correctly sized, or they are correctly sized, but they are just differently sized. So what we did is we started to look into the architecture of the whole environment, and then we said, okay, let's group things together and understand when to power on something in a particular order. So if you have a batch power on, we understand the optimal way of placing these workloads on the infrastructure so that you don't have locked capacity. Think about, I'm starting up with a 2 GPU configuration, and again, another 2 GPU configuration. If you look at this environment, you will see that some of these environments are grouped together or not. If we then start to say load balance across NUMA nodes, and we do 2 here, and we do 2 there, we still have 4 GPUs available, but we cannot map those 4 together. So this is something we do in DRS in the host. We understand that hey, we're going to place them in such a way that we always keep the most optimal or the most largest configuration available for the next power on. Does that make sense? Okay, cool. Back to you.
Is it?
I think it is.
Oh, no. Yeah?
Yeah.
Oh, right.
Good to you.
So when to scale up or when to scale out. So when to choose a bigger model, more GPUs, or scale out depending on the type of architecture. There's a ton of different metrics to take into account to start with initial sizing. And to basically, get to a model in which you can predict scaling. And it's very hard to predict scaling for AI. I mean, looking back, like if you deploy a traditional application, could be modern, but like an application, you expose it to your first business unit, they start to use it, they kind of find a success, and you basically scale it out to other business units as well. What we've seen in the past with AI workloads, is that as soon as an AI workload, an AI application is being successful, it's not scaling out linearly, it's probably scaling out exponentially because of the popularity. Look at an average ChatGPT kind of application, like a RAG app. As soon as people know it exists within your company, everyone wants to use it. So scaling out could become an issue, and that's definitely something we need to take into account. And we found out in the last couple of years that sizing and scaling is quite hard. If you would size an infrastructure for a traditional database, you kind of know what to size for, right? So the size of the database, the cache, the number of end users, the number of concurrent sessions. And that's kind of basically, well, it's a little bit more complex, but that's kind of it, right? If you take a model, there's many more parameters to take into account to get to a successful sizing. And if you look at kind of the important metrics to take into account, there's a large number. That's the size, it's the precision, it's the number of layers, the latency, the KV cache size per token, the number of concurrent sessions, the context length window, so the number of tokens a second that you get presented in your session. The sequence length, the first time to token latency, really important. I ask a question and I don't want it to take like 30 seconds before I get an answer. Or maybe I do, I don't know. The VRAM requirements, the GPU precision capabilities, NVLink or FV-switch support, the tokens a second throughput, NVRAM bandwidth, it's a lot. Teraflops a second of my GPU. So I've been spending the last 15 years or so, 10 to 15 years, on sizing a lot of infrastructures for GPU usage, but mostly from a VDI perspective. And that was relatively, I would say easy, but doable. There's a lot of similarities to what we're doing here, but it can be a lot simpler. So we had a ton of conversations about this, different kind of customer scenarios, different types of workloads, types of models. How can we simplify the sizing methodology used and basically offer you kind of a number? Like here's a number of settings that you need to adjust, and then sizing is done. So it's time for the demo, and we're doing it live.
Yeah.
If all goes well.
Of course it is. Yeah, I already did.
Oh, yeah, we're there.
Yeah.
So I'm going to show you a different sizing calculator first. So this is one that's already on the market. It's from inference.io AI. It's a commercial company. I think it's a service provider. They call themselves a neo cloud nowadays, and they offer such a calculator. It works really well, but from an IT admin perspective, I need a ton of information. I need to find out, retrieve from somewhere, Google for it. I don't know. And based on the information you add, you get a result, right? We thought that could be a lot simpler. So what we did is build this thing. It's currently in public beta, which means there's a URL there. You could try it out yourself. There's a couple of caveats, and I'll share them in a bit. But what I simply do here is search for a model, Quen. Let's say Quen.
How do you get that information?
Yeah, so this is really cool. I build an API that interacts with Hugging Face. So all model information that's publicly available at Hugging Face is structured in a way that you could retrieve it through their API. So I'm basically just dynamically approaching the API, retrieve that information, and
to give a little bit of extra information, Hugging Face is the online repository, the leading online repository for open source models. So it's basically the GitHub for models.
Yeah. So if I would select like the second one, Quen3-coder-30BA3B instruct. So this is like the namespace in which a model is named, right? So this is the universal name used to deploy the model and to download it as well. If I just select it, next thing happens. There's some static information, and Frank talked about the minimum GPU usage of when you deploy a model. So that's the static memory usage that's already calculated. And we retrieve that information from Hugging Face. Then there's a first time to token latency, which is a second right now, and a standardized KV cache size based on FP16 precision. Now what I can do
is... So to add more a little bit, sorry, I think Johan is selling himself short on this one. So what Johan did was he took the API, he basically said to Hugging Face, give me the information from this model, but without downloading it. Yeah. And so I'm going to analyze the architecture of the model, and I'm going to use that information in order for you to really understand it before you actually do some action. And so that's where you're at right now. So you have the information, but you don't have to have any inbound files coming in.
Yeah, right. And the most important requirement why we build this like this is that there's new models every hour. Or like if you look at Hugging Face, there are a gazillion models, and new ones are being deployed like on a very regular basis. So I didn't want to build something static. I just wanted to pull that model information from, the model that you actually want to use, and that's available today, right now. This is the requirement when I deploy that model. I have a context window, a context length of 400 tokens, and a single concurrent session. That's nice for a POC or for testing it out, but when I want to scale it up, I need to adjust those digits. So looking at the type of GPU that's recommended right now, and I'm still working a little bit on the recommendation engine, but it suggests an A100 with 80 gigs simply because that GPU has 80 gigs of frame buffer, and it allows for 1,000 tokens a second to be processed. If I would adjust the context length right now, what you'll see, if I exceed the 1,000 tokens, it automatically switches to a different GPU that allows for 1,583 tokens a second.
So to, again, give you me a little more props. So it's 80 gig, so that's everybody can understand that. But when you say, okay, I've got now this new RTX card that's coming out, right? And it's got 96 gigs, but I also have an NVL H100. Which one should I use? That's basically depending on the number of CUDA cores in the system, the number of computational power it has. And so what you see right here is then based on the tokens, we can actually understand based on the architecture of the card, how fast you can get it, right? So it's architecture of model with architecture of the GPU.
Yeah, and if I would add now the number of sessions, let's say support 3 concurrent sessions, which means I'm supporting 3 times 1227 tokens a second, you automatically see that it switches to a different GPU. But what if I exceed the capacity of a single GPU? Well, it's fairly simple. It suggests me to use NVLink instead. So the more I add, the different the suggestion would be. So there are a couple of things that I'm still working on, but I'll dive into that in a bit. What was really cool, who was in the session before with William and Alan Renouf talking, like, cool. So they briefly talked about private AI as well. And I'm in a lucky position to have a data center capable GPU in my lab, in my home lab, but not everyone has that. So one of the cool things is, if I just dive into another model, looking at, there is a Gemma 3 270 million parameter model. And you can easily see, if I switch to a different model, that the minimum memory used is half a gigabyte, which means, and the headline of the news item was, you can run this model on a toaster. I don't know what kind of toaster it was, but yeah. I had a chat with someone from Google yesterday showing me a Pixel that ran that model. So it's locally running on the phone. So nowadays you don't always need a GPU to run such a model. And this is just the explanation. So I'm also working on getting, if you want to run this on CPU instead of GPU, add a sizing recommendation there as well. Any questions on this?
Yeah, poor observation. This is awesome. I think it's a big round of applause. Yeah.
Cool. So you can test it yourself. There are some things that currently don't work. And let me go back to the slides to show that. Right, so yeah, we saw that all.
You spoke around and you tell them what GPU have and tell
I've tested a lot of stuff. I don't want to brag, but I got a couple of A6000s, a couple of L40Ss, H100, A100. Some of them are in the ITQ lab, some are in my home lab. An L4, which is really cool, but you can buy a second-hand P4 on eBay nowadays for $100, and it has 8 gigs of frame buffer, so it will run some of the models perfectly fine on the GPU. So there's some roadmap items. So most models can be queried right now, but there are some models that can't, and that's simply because some are gated. If you look at OpenAI models, they need to have an authorization to deploy Llama, to download Llama. So that's a personalized authorization, which is not allowed by the tool right now. And the Mistral models are the same ones. So they are gated. You need to register. You need to authorize. You get an API key. And one of the things I'm currently working on is for you to deploy your own or load your own API key in the tool. And basically, based on your own API key, you do get the sizing information and the metadata. Second thing is that I want to add a feedback loop, because this is theoretical. The sizing is theoretical. But if we can submit a validation button or add a validation button whenever you test it, you validated that the sizing that was proposed has been validated and does work, other people could kind of check that sizing and take that for granted. Currently, it does support inference, That's the only workload it supports right now, because training does require different capabilities of your GPU. And it's based on a lot of RAG models. But what if I do real-time object recognition in video streams? That does require something else from my environment, not just a GPU with GPU memory, but also encoders or decoders. So that's also something that I'm currently working on. And agentic AI, like if I want to deploy multiple models, like what does that look like? Frank talked about mixture of experts. So if we have multiple experts in a single model, already in a beta version have that running, it works really well, but it does require different things from the KV cache. And this is really interesting. Models come or could come with a system prompt, which basically states if you load the model, you add your first prompt, you could get a prompt back from the RAG application. And what that does is already with every session that's being started, it generates maybe 2,000 tokens upfront, which impacts the number of sessions you have on a single basis. So that system prompt information is also part of the metadata of Hugging Face. So it's just a matter of populating it. But I'm also working on that. So if you like to participate in testing, you can drop me an email or reach out to the URL gpusizer.johan.ml. In the near future, we're probably gonna put it behind a different URL. But yeah, if you follow me on LinkedIn, you'll be the first to hear about future versions.
Cool. So I think we're out of time. So please take the survey, helps us. And, oh, sorry, I would like to abundantly thank you all for attending.
Yeah.